Okay, so it's a pleasure to welcome back Josh for his next talk.
Oh, great, thank you. Yeah, it's a pleasure to be back. It sounds like the mic is working just fine. Last time, what did we talk about? We talked about some series related to lattice enumeration. The theme of this mini course that I'm giving is on lattices and Tableaux. We haven't yet seen Tableaux, well, in this lecture. We've seen them in Amri's lectures. But we've certainly seen some lattices. And I've been working a lot with matrices, and I'll continue to do that. But I also won't be afraid to be talking about lattices as well. Okay? From last time, I mentioned two series, right? We have this one, the Agusa function, okay, relative to n there. And we saw this in the context of elementary divisor types of lattices, okay? So this is a series that goes hand in hand with elementary divisor types of lattices, and that's why it's appeared in so many different works. I didn't give any references, but there are a few people here that have had this appear in their papers. So I could list some references, but I don't want to do that right now. Though if you have questions, feel free to ask. We also talked about this series, which I introduced, called the Hermite-Smith, and it's recording the elementary divisor type as a composition, not a partition. That's what this inc is, increments, okay, of a lattice lambda. And the, what were we calling this? The Hermite composition, delta, okay? And there was some discussion about normal forms, and just remember that all I really cared about was these diagonal entries of that Hermite matrix, okay? So this is relative to a flag, and that's gonna come back in today at some point, okay? So there we have a complete isolated flag in ZP. Okay, so I'll continue on, and this time we're gonna talk about sort of the mother, so to speak, right? So I've introduced you to some friends of mine, and now we're gonna meet the whole family, okay? And we're gonna start off with meeting the mother. Right, so I wanna set up a bit of notation, all right? So partitions, I mentioned this last time, I won't say much more, but it's actually a little bit more convenient to think of a partition lambda as an infinite sequence, lambda I, non-negative integer, and of course I want this to be I want this to converge to 0, and I want it to be monotonically converging to 0. Okay, so all but finitely many terms are 0, and as usual, it's so on. Okay, that's just a bit of a convenience there. Okay, and we'll start talking about Tableaux right away. Remember from Amri's talk, Amri gave two definitions of a Tableau. Okay, I'll record some keywords. One of the definitions was the sort of filling of a Young diagram, satisfying some properties. Okay, that was namely, it was weakly increasing along a particular row. Weakly meaning you're allowed to have multiple of the same so long as you don't go down, so non-decreasing if you like. And along a column, it was strictly increasing, okay? We're not talking about LR Tableau, we don't need this LR condition, okay? We also saw another definition. These are given by flags of partitions with some more properties, namely consecutive partitions give you what's called a horizontal strip. I'll come back to that one a little bit later, but for now I just want to think about fillings of a Young diagram, okay? So I'll put an example up on the board. Probably come back to this later. I know Amri said that experts don't draw boxes, so that might mean that I'm not an expert, but there we are. I like my boxes. Okay, so here's a Tableau T. Let's call this T. Okay, and it has a shape. And a shape, we talked about this last time, but I'm giving it a bit of notation here. SH. And that shape you read by the corresponding Young diagram here. So that would be 55311. Okay. We'll come back to this tableau when we want to do some examples for the definitions I'm going to introduce. Okay, I want to define SSYT sub n. This is going to be the set. This is the set of all Tableaux. And I should mention, I haven't actually. I'm using the word Tableau, but many other people will call these semi-standard Young Tableau. Semi-standard Young Tableau. That's where this SSYT is coming in right here. But I don't want to use that many words, so I'm just going to call them Tableau. The set of all Tableaux with labels in the set 1 to n, or my notation bracket n, as Angela reminded us of this morning. Labels, what do I mean by that? The labels are these numbers right here. Okay? So this could be in SSYT 7, there's a 7 here, or any other larger number than 7. Okay? So it's an infinite set. This is an infinite set. Okay? We can just continue, I could just continue to add 5, 6 to this forever, and it would be an infinite set. All right? Now what I want a very particular definition, and for our discussion, what's very important for us are columns of tableaux. Columns inside of a tableau, sorry. Columns of a tableau. So I want to say, we'll call a tableau reduced if it has no repeated columns. Okay? And this tableau in this example is in fact reduced. There are no repeated columns. Okay? But I could do this 5, 6 right here. I'll write it a little bit lightly. I'll erase that because I won't need it. That would no longer be reduced because now we have a repeated column. Okay? That's no longer reduced, but once I get rid of that, that would be reduced. Okay? And the corresponding set of Tableaux, the corresponding version of this, will be, I'll use a lowercase r, SSYT, n, reduced. Okay? This is an infinite set. This is a finite set. Okay, the trick of extending by adding the same column over and over no longer works here. The finite set. Okay. As I mentioned, columns are very important. I need some notation. It'll be very useful for a tableau. Now, I typically like to say, I'll write this, T sub I, j. That's going to be the natural number in the cell I comma j. My convention is similar to matrices. Let's use some color. I think orange might be good enough. So this would be row 1, 2, 3, etc., just like in a matrix, column 1, column 2, column 3. Okay, so Tij would be in the ij cell if I'm thinking of this as a matrix. Okay, it might not exist. Anytime I refer to a Tij, I'll assume that if it exists, and if not, then the condition will just be not important at all. Okay, so Tij is the ij cell, and what we're going to do is we're going to write T as a sequence, C1, C2, C for column, where Ci is a subset of n. Okay, and here I'm implicitly assuming that T is a set as a tableau inside of SSYTN here. That way I can say this. Okay, these are the columns. These Ci are the columns. So in particular, C sub I is the ith column of the tableau. Okay, so in this particular example here, if I were to, I'll just write a few terms, not all of them, of course. The first set would be 1, 2, 3, 5, 7, and then you can fill in the rest, okay? It has 5 columns that we can see. Okay, what else do I want to say about columns? Yeah, one more thing. We're going to write C in T to mean that this set is a column of T, okay? This means C is a column of T, some Tableau T. Okay? As I said, columns are going to be very important when we talk about these Hall-Littlewood-Schubert series, as you'll see very soon. Okay, and I need to set up some notation. Okay, so I don't care by this notation. I'm not saying that I'm not giving it a particular index. I'm just saying it is a column of this Tableau. Questions on the notation? Okay, let's build off of it then. HLS. Right. So we're going to define a set associated to a Tableau, the leg set of T, and T is, I'm always just going to assume now it's an SSY T sub n, is the following. Leg sub T plus of ij. I'll maybe say I and j are just natural numbers. Okay, we have a case distinction to make. Cj, meaning the jth column of T. Cj intersect the interval of discrete values Tij, Tij plus 1. If Tij plus 1 is not in Cj, empty otherwise. Okay, this might be a bit if you're like me, it's a bit kind of tricky to understand what this is really getting at. We're going to do some examples, but not just yet. Not just yet. We won't do some examples. I want to get you to the definition of HLS, and then we'll see some examples. Yeah, I can, and I will. I'll be looking at various I and J's for that. Yeah, indeed. Good. If you know a thing or two about legs in terms of Tableau, this is coming from that notion of a leg. If you're thinking of the hook length formula, yeah, it's called hook length formula. You'll have a notion of a leg there. It's sort of inspired from this. We'll see that a bit later too. Okay. I want to define another set, L sub T. L sub T. This is just going to keep track of those I and J's where this is not empty. Okay? Very simple. Just going to keep track of all those I's and J's where leg is not empty. Okay, I could write it differently. Equivalently, I could just put in this condition, right, into here, and that would be okay. But for me, the way you should think about this set right here is that this is just recording those I's and J's where this is not empty. Okay? This will be an important set for this wonderful polynomial. The leg polynomial of T is as follows. Okay? Capital phi sub T and a variable y is going to be a product. Running over all the I's and J's in this set down here. Okay? And what we've got is a wonderful expression. Okay? Got that. You might see now why I might care about when the leg is non-empty. When it is empty, then this would just immediately be 0, and it wouldn't be very interesting of a polynomial. At least not for what I want to do with it. Okay, so the necessity of the LT is only to make sure that this is non-zero. This is always a non-zero polynomial. And after sitting in Amrit's talks, I think this has something to do with maximal elements of a particular ideal in the fundamental post set. I don't yet know the direct connection, but there seems to be a connection there. So I'm just going to leave it at that. Okay, I'll use this side of the board. All right, definition, HLS, and then we'll do some examples. All right, the HLS series. The Hall, Littlewood, Schubert series is as follows. I'll just write an underline here. I'll explain what those variables are. We have one variable y and many variables x, one for each non-empty subset of n, the set bracket n, sorry. Okay, and it's a sum of all tableaux in SSYT sub n, infinite sum here, of these leg polynomials, together with running over all columns of the tableau, x sub c. Okay. That is HLS. Okay. It's running through all the semi-standard Young tableau and picking up, weighting it by these leg polynomials. Okay. Exercise. This is a finite sum over the reduced tableau. R SSYT sub n of the same polynomial. Now, instead of products of terms of monomials here, I have geometric progressions. So that already might tell you something about this leg polynomial. Yeah. I crossed the line. I shouldn't do that. Okay. So that's HLS. HLS is, well, it's the mother. You can think of it as an infinite sum. Sometimes this is useful if you want to think about a particular tableau. But oftentimes I like to use the work with a finite object, and there I'm thinking about reduced tableau. Yes. No, I mean a column here. Yeah, I do mean a column. Yeah, indeed. Yeah, we're working with subsets, and I'm really using the fact that a tableau will always be strictly increasing going down. So I really won't get any repeats, and it really will be a subset. Yeah. 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 Yes, 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 yes. This polynomial will still be a polynomial, and it doesn't matter how many repetitions you have. In fact, what this exercise is it's showing that actually, if you reduce the tableau, t, you actually don't change this polynomial at all. So you have exactly the same polynomial after reducing. That's essentially what this exercise is, once you do that.
The number of variables is 2 to the power.
-1, because we're not keeping track of the empty set. +1 for y, fine, yeah. Yeah.
Oh,
so
y.
to the n minus 1 x's, +1 for y. Yes. Exactly. Yeah. If t, indeed, if for example, yeah. Okay. The question was if tij is equal to t. I think this is what you're asking. Tij plus 1. Then you would in fact have this element inside of this column. This is in the jth column, as we can see here. So this condition would be false. You would have this in there, and therefore it would be empty. Yeah. Oh, we worked out one part of that exercise. Very good. I'll leave that example there, because now I want to do some examples. Now, there are some families where, the mom is a bit crazy. I'll leave it to you to judge that. I think she's quite nice. This is Very, very welcoming mother. Anyway, all right, enough family jokes. I want to use the same tableau here, okay? So let's look at the L sub t here. Okay, so the L sub t, let's use some color. Okay, we'll try these. I think I have an orange over there. Good. Okay. L sub t. Right. So what are we keeping track with L sub t? We're looking at those I and j's where this is non-empty. Namely, we're looking at those i's and j's where this is true. Okay, there's a negation there, but let's work this out. Okay, so we'll start with 1, 1. The one entry right here, the very top left, we see to its right a 1. That's the ti j plus 1. And of course, this number is in this column. So this ij, as in 1, 1, will have an empty leg set. Okay? And in fact, you can see that's going to be true for all of these values right here. For example, 2, we'll see a 3, and that 3 is in here. 3, we'll see the 5, and that 5 is in here. And as I said, when a cell doesn't exist, we just ignore it, and so there's no cell over here, so we're just going to not worry about those there. They have no contribution, okay? So the leg set for this whole column is empty. Now, let's go here. In the 1, 2 position, we look to 2. 2 is not in this column, and that leg set is going to correspond to just this element right here. The elements of this column that are in between in value 1 and 2, inclusive. Only have the 1 there, okay? Likewise, if I look at the 3, I look to the right, I have a 4. 4 does not appear in this column. I've got a leg there, a leg set there, but it doesn't go to 5 because 5 is greater than 4. And the same actually happens here. I look to the 6 and there's nothing below, so it's just that. Okay, we look below, that's where the leg is coming from, by the way. Right, I look to the 2 and I see the 3. The 3 doesn't appear in this column, but 4 is greater than 3, so we're done. 4 sees the 4, so we don't worry about it, and there's no column there. Okay, 3 sees the 5, and the 5 is both bigger than 3 and 4, so we get a set of size 2 there, a leg of size 2. Okay, and lastly, 4 and 6, we get that. Okay, so I guess I only used red, but there we are. What were those? 1, 2, 1, 3, 1, 4, and 3 others. 2, 2, 2, 4, and 3, 2. Yeah. Okay. Those are the ij's where the leg set is non-empty. Now we can write out this leg polynomial for this tableau right over there. Okay, all the leg sets, have cardinality 1 except for 1, and that is cardinality 2. So we've got 1 minus y, 6, so that's 5, 1 minus y squared. There's the leg polynomial. Okay. All right. There'll be some more examples and exercises in the tutorial, but I'll leave it with this. Okay, let's take a look at HLS. We can look at HLS for at least n equals 1 and 2. I'll write those examples down. HLS 1, I guess it's in 2 variables. This is very simple. Nothing too complicated there. HLS 2 is also great. Well, actually, they're all great, but I'm biased. So we get that as our numerator, 1 minus y, x1, x2. The values here are corresponding to sets, the singleton 1, the singleton 2, and then we have 3 factors in the denominator, corresponding to the singleton 1, the singleton 2, and then the set 1, 2. Okay. We don't keep track of the empty set, and we only have 3 non-empty subsets. Okay. So those of you that have worked with functional equations or self-reciprocity might be seeing something already. I want to record a wonderful theorem that Christopher and I proved concerning these HLS. By this one right here. I mean, this is my shorthand for, yeah, each subset has a variable there. Yeah. Other questions? All right. Right. So self-reciprocity. Yeah. Theorem. Self-reciprocity. This has a wonderful. What I mean by this is I'm inverting all the variables in the x. Okay? So all of those variables are inverted, and we have a -1 to the n, y to the minus n choose 2. We get an extra x variable here, and that's corresponding to the full set, 1 through n. And then we get our HLS. So I call this self-reciprocity when I'm dealing with a combinatorial Denef formula, functional equation when I turn it into a zeta function of some sort, or maybe a Dirichlet series, I'll call it.
Does it have anything to do with lattice enumeration?
What? HLS?
The self-reciprocity.
Self-reciprocity? Oh, yeah, sure. Wait. Is the same question, can I prove self-reciprocity by means of lattice enumeration?
Yeah.
In a sense, that's sort of what we did. In a sense, that's sort of what we did, actually. I'll say a little bit about this. I do want to say, there should be a combinatorial proof for this. Should is perhaps strong. I would be interested in a combinatorial proof. I would be interested if one could do this perhaps using Tableaux just by themselves or something like this. Yeah, Amit, you were saying something.
Weaker than saying there is.
What?
Weaker than saying there is.
Yeah, indeed. Yeah, I certainly don't have a combinatorial proof. Whatever combinatorial proof might even mean, one could argue that the proof that Christopher and I gave is a combinatorial proof. Okay, fine. I won't get into that. But I do want to say a little bit about how we proved this because the ideas are really quite nice. And we saw this in Tobias's lecture yesterday, some of these ideas. Okay, so how did we prove this? I won't prove it. Recall that the determinant of M, now we're going back to matrices here, and we're thinking about lattices and Smith normal form. Okay, a bit of a mouthful there. The determinant of M was what? It was always P to the lambda 1 plus all the way down to lambda n. Right? And what else do I want to say? Oh, yeah, right? We have that. And if I were to take actually valuations, p-adic valuations, we can just drop the p. Take the log base p, yeah? So we have that as the valuation of the determinant. And actually what we can do is we can recover all the parts of this partition. We can recover all parts of lambda, parts being the non-zero terms of this sequence, by looking, or computing if one really forces me to, by looking at the minimal valuation of various minors, of all I by I minors of M, okay? Now, it's not going to be direct, just as we see here. Instead, what we'll get from that, the minimum, will be, let's see if I can recall. So, homework for me. I think Tobias was using the F sub I for the set of all minors of M. But if not, that's what I'm using now. And maybe I should put a p-adic valuation there. The minimum here will give me lambda 1 all the way down to lambda n, okay? And then, of course, once we have all of these, we can get each of the parts here. And that's essentially what we do. Now, you have to be very delicate because it's not just one particular partition we're looking at. We're looking at a number of partitions. And now I want you to remember now what Amri said about Tableaux as being flags of partitions. Well, we have like n partitions that we need to care about. And it requires a bit of delicate combining, unioning of various sets of homogeneous polynomials there. Okay, I'll spare you those details, but it's essentially at the end, it's a p-adic integral. Yeah, 1 second, let me just finish this thought. Over zp n plus 1 over 2 of sets of homogeneous polynomials. Okay, that's all I want to say about how we proved it. But what's a really key idea is that you get this Smith form, the Smith partition, by looking at minors and matrices. Sorry, there was a question. Yeah. Yeah, lambda I plus 1 all the way down to lambda n. No. I have n minus I, the way I'm working with it. So 1 by 1 minors. I see. Yes. Thank you. You're right. Yeah, if I was looking at 1 by 1 minors, I would only pick up the lambda n. Yeah, so one needs to fix this. Perhaps it's n plus 1 minus I, but yeah, there should be n summands here, whatever the right thing is. I summand, sorry. Good. Other questions? Yeah. Yeah. M is a matrix that I didn't define. It's just some lattice coming in, but it has some elementary divisor type given by the partition lambda 1 through lambda n.
There's something connecting nature.
Yeah, and that I will get to eventually. Yeah. The question. Okay. All right. So why am I bringing up HLS? Well, I hope I said yesterday that the only way I know how to understand this as a rational function is to work with Tableaux. And now, more specifically, now that we've met HLS, it's actually only through HLS that I know how to understand this HS function. Okay? Well, yeah, I want to say a little bit about that. How do Tableaux help us understand HS? I want to say this, I want to make this very clear. Tableaux are a finer object than we need, than needed for HS. Okay? And I'll be very specific about what I mean by that, but I have to erase. Okay? What do I mean? I mean, remember this map from the other day. H, the Hermite form of a lattice, we were going to map that to, we're looking at the fiber sizes of lambda of H and delta of H. Okay? And I remember I don't really care about the form, I only really care about the diagonal entries there. What we're going to do is actually map this up over to a tableau. And I'm going to write this as tableau, I'll just put T of H. Okay? That's going to factor down into here. Now, how does a tableau give us these two pieces of information? Let's go back to what we know. Tableaux have what? They have a shape. And I believe Amri talked about this. They have a weight vector. I'll say it just in case it's been a while. A weight vector is the vector that counts the occurrences of the labels. So the shape of T is 5, 5, 3, 1, 1. That's a partition, all right, because it's a Young diagram. The Young diagram comes from a partition. The weight vector of T, I'll just use W, is going to count the occurrences of the labels. So I'll have a 2 in the first position because there are 2 1s. I will have another 2 because there are 2 2s. I'll have a 3 in the next coordinate because there are 3 3s. There are 2 4s, 1, 2, 3 5s, 2 6s, and 1 7. Okay, that would be the weight vector. This is what is recorded by the Tableaux for associated to a lattice. I haven't said how to associate that Tableaux yet to the lattice, but the essence is Tableaux, the shape goes together with the Smith partition, and the weight goes together with the Hermite composition. Okay? That's what I mean by it's finer data. We're not using, it's not a one-to-one thing. There are multiple Tableaux that have the same shape and weight vectors. Okay? So it's slightly, Tableaux are slightly finer for HS, but it's just the right object we need for a series that I'll talk about very soon. Not in this lecture, but after lunch. Okay. So how does this help us? This? Yeah, of course. Ah, yes. Yes.
You said it in the other way. You said combinatorial identity.
Yes.
And you prove it using counting problem.
Yes. So you want to know how HLS is maybe connected to HS? Because that's what's coming next. I'm gonna tell you how we get from HLS to HS. Why is HLS here? What are we doing with it? I think I'll erase this example now. Yeah, so where we start, we started with lattices. We saw that we had normal forms, Hermite and Smith. We saw the success of both of those invariants in terms of lattice enumeration. In particular, we looked at the subgroup zeta function associated to zp to the n. And we saw that it was a substitution of the Gusa function. This Gusa function, morally, is keeping track of the elementary divisors. Okay? This came from the Birkhoff, this sort of factor. Of course, there are the other interpretations as well. This was, I kind of view this as the Birkhoff coefficient, and this was keeping track of the number, the fiber sizes of when you take a lattice and you map it to a partition, i.e. through its elementary divisors. Here now we're keeping track of two of the two pieces of data simultaneously, okay? And now HLS has come in. How does HLS relate to this counting problem that we started with? And that's the following theorem. Sorry. I need notation. Sorry for the cliffhanger. I need notation. Hold on. That's why I write notes. Otherwise, I get too excited and just tell you the theorems without any notation. So let me set up some notation, and then I'll get to the theorem. C is a subset of N, okay? The dimension of the Schubert variety, say a little bit about this after lunch, associated with C it'll be denoted by D sub n of C, and that's the following value. I'm going to take a sum. I'm going to run through all I in the complement of C. And I'm just going to sum those i's up. Okay. So this is, you can think of this as like a major index of sorts. Angela described this major index. Of course, there's no descent set here, though maybe you can think about it like that. Minus a binomial coefficient, n plus 1 minus the cardinality of C over 2. That's on its own. Okay, this is the value of the dimension of the Schubert variety. And Angela was so kind to remind us the dimension of the Grassmannian this morning, right? That's the thing I told you to pay attention to yesterday, the I times n minus I. Right, we saw that come in right here when we evaluated this to get the subgroup zeta function, zp to the n. This is the analog I was talking about. We'll see how. We'll crystallize that analogy soon. Okay. Oh, with that same C, let y underscore C be the product of all I in C of the little yi's. Right, my little variables here. Okay, now I think I'm ready. Got just about enough. The Schubert dimension will come in beyond just this theorem and beyond just HS. I'm going to define an involution on subsets of n, and that will be what? That will be n plus 1 minus I for all I in C. Same cardinality. I'm just sort of flipping the numbers in some sense. Okay, then we have the following. Let me find that theorem. There we are. HSN ZP, variables x and y, is a substitution of HLS. Namely, I take p minus 1 for the, it's not there, it's over there, for the variable y, the single variable y, and then for each subset, I'm going to put in a p to the dn of c. That's the analog of the Grassmannian dimension when we plugged it into the Igusa, times some variable, a single variable x, subcardinality of C. Remember, I have 2n variables over here. You're going to soon learn I'm not afraid of having lots and lots of variables. If you haven't already, I've got n variables of x's and n variables of y's. Those are my x's. I have just one for each C. And then for the y's, I have a product of those, and that's going to be where that C star comes in. That's for all non-empty subsets C in 1 to n. There we are. So you see that when I look at Hermite-Smith series, I can think of it totally in terms of Tableaux. Okay? And the ideas to that, this proof, well, actually, the proof of this, I only know how to prove this by counting a harder problem and specializing. We're going to see that harder problem soon. Not right now, but after lunch. But when you want to look at these two values, these two pieces of data, the elementary divisors and the Smith, the Hermite parameters, the diagonal entries on that Hermite form, you're really looking at a tableau based on its shape and its weight. This is a Casca flavor to that. I specialize what to be 1? X to be 1, yeah. Yes. Do I get sum of Schur polynomials? Yeah, you can think of it that way. Now, I don't know. It might, I don't know if it will be exactly sum of Schur polynomials on this side of things. Let me think about it this way. This is really kind of the only way I know how to think about this. Yeah, you're going to get a sum of sure polynomials. If you set all the x's to 1, yeah, you're going to get a sum of sure polynomials. Yes, and now that I think about it, this is an exercise. This is what I deem a somewhat challenging exercise, but perhaps for you it's might be a triviality since you know about sure polynomials. Yeah. Once you know the symmetric function theory, yeah. I mean, for those that don't, it's not so simple. But just from this alone, I'd say it's less obvious. And in fact, you have to do a little bit to see that, and that's where the exercise is. But it's coming to that. It's coming to that idea that you see. There is a connection indeed, which is the root, the reason why we throw in Hall-Littlewood. Actually, there's a connection to Hall-Littlewood polynomials here. I want to explore this just a little bit through examples. I don't have much time, but yeah, this is great and all, but how do we see this on the level of lattices? And well, I won't do it all, but I want to consider two tableaux of the same shape and same weight vectors, but two different tableaux. T1, 1, 3, 2, and T2, 1, 2, 3. This might be the smallest example where we get a collision like this. Okay, so we can see the same shape, yeah, 2, 1. We see the same weight vector, 1, 1, 1. I haven't told you how to associate a tableau with a lattice, by the way. We're going to get to that after lunch. But what we could do is we could look at the term of t in this infinite series right here. Okay, let's do that. So the leg polynomial, another example of that. There's no reason to look at any of these two. There's only 1, 1 to look at. And the 3 sees both of these, but the 2 only sees one of these. So the T1 term would look like phi, there'll be a phi and then some variables. And what will those be? The phi function in this example is y squared, and the two variables associated with it are x12 times x3. I'll put that an arrow there. And then the term of T2 inside of that infinite series will be 1 minus y, x13, x2. And those correspond to one another. Okay. So, of course, in HLS, these are two different terms, but if we look at the HS substitution, the HS substitution given by this right here, okay, what we need to do is we need to compute some data. Just do that pretty quickly. We have 4 sets to think about. We have the 1, 2, and the 3. Put a double line here. This is the T1 side, this is the T2 side. We have a 1, 3, and a 2. Okay? It's not 12 and 13, rather it's the set 1, 2. We need to compute the C star, and we need to compute the dn of C. Okay? I'll just give it to you due to time reasons. We get a 2, 3 for this. We get a 1, 3, and a 2, right, by performing this little involution. For the DNC, the dimension of this Schubert variety, you can compute that fairly easily. That's a 2, 0, 1, 1. Okay. Don't need this anymore. Right, now if we put this substitution in, that the theorem asserts, we get the following. Now I'm gonna apply the substitution to both these terms individually. I'll have a 1 minus p to the minus 2. Okay, that's the y going to p to the minus 1 over here. And now I'm going to, for each set, I'm going to also incorporate the p to the dimension. So I'm going to get another p squared for both of those. x12. That's going to go to what? That's going to go to an x sub 2, because it has cardinality 2, and the y star is going to be given by that. Okay? So I'm going to have a little x1, a little x2, because I have a set of cardinality 1, a set of cardinality 2, and I'm going to get all three, y1, y2, y3. All right? The union of these is 1, 2, and 3. Likewise, if I look at the other term, I'll do it a bit faster now. P to the minus 1, I also get a p squared, the sum of 1 and 1. But 1, 2, y1, y2, y3. Okay, the claim is oh, it didn't shout. Okay, well, there it is. The last thing I want to say, the claim, there are what is the number? 2p squared minus p minus 1 matrices of the following form. As some Hermite normal form, given as p, 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 question mark, question mark, question mark, i.e. fill in the rest, with Smith normal form, 1p, p squared. Okay? By the end of the next lecture, I hope we'll see how to do this. These are question marks. Thank you.
Questions?
You said you can associate the shape as well as the weight. Shape corresponds to Smith and weight corresponds to Hermite. So if you have a lattice in ZP power and take the Hermite, how will we associate the weights using the Hermite form?
The weights, how do you get that? I'll make this very precise after lunch, but I'll tell you. You have a diagonal of p powers, right? And those exponents I'm going to care about. You read this way. So the weight vector will be the first entry, second entry, third entry. In this case, 1, 1, 1 is no coincidence.
And what about 2, 3, the other weights? Oh, just like
the whole thing, the whole diagonal
okay.
is the weight vector. Yeah. But read from bottom to top. Okay. Well, sometimes. Okay. I'll make that precise too.
Okay, any others? Right, in that case, let's thank Josh again.